Across Europe, drones are increasingly present in fields, forests, and rural communities, but their real impact depends on how innovation connects with real needs on the ground. The Icaerus podcast series explores how this connection is built through research, use cases, and collaboration with innovators and end users across Europe. I am Dimitra Furkalidou from Reframe.food, and in this episode, I am joined by Bruno Barrionuevo, a researcher at GeoSense. Welcome, Bruno.
Hello, thank you very much for having me. It's a pleasure.
Thank you very much for being here. Today we will be talking with Bruno about life cycle assessment, or LCA, what it is, how it works, and why it matters when evaluating the environmental performance of drone applications within the Icaerus project. So Bruno, to start us off and make sure that we are all on the same page regarding that, what exactly is life cycle assessment?
Life cycle assessment, or LCA for short, is basically a methodology that we use as a tool that allows us to determine the real environmental footprint of anything we want, whether it's a product, a service, even a company or organization, by looking at not just this object or service in itself, but also considering everything that comes before this was produced or generated, and also after we have made use of it. Maybe let's use like a common daily example that may help us all to understand a bit better what we're talking about. Let's say we take a loaf of bread, something we all have in our houses very often. When we look at it, we intuitively know that this has some impacts on the environment. However, in order to know really what that impact is, we need to take into account the whole story of this loaf of bread. And this story doesn't start in the bakery where they made it and we bought it, not even in the field where the wheat was produced. We need to go even further back. This story probably begins with everything that is needed to make this field of wheat productive. This means seeds that needs to be bred and processed. It means fertilizers. It means any production product, fungicides, pesticides, etc. All the energy that is required at each step to produce and transport all these things, as well as the equipment, for instance, that needs to be used in the field, which in its turn requires many elements related to steel, plastic, energy for its manufacturing, etc. From there, we take into account all these elements, then we can move on to the wheat field in itself, when many things are done in order to produce this grain. From there, this grain will also move to a mill, where it will be grinded to produce flour, that in turn will be packaged, transported, and sold to a bakery that will produce our bread. Through all these steps, energy is being used in different ways, from electricity, fuels, materials, each of them with its own environmental footprint. So LCA basically what tries is to capture this full chain of, if you want, cause and effect, showing us how these impacts on the environment accumulate from the very first inputs all the way to the final product or service that we are assessing. And in this way, LCA helps us to see where the real impacts come from, where this product or service is really affecting the environment and in which way. And in this way, we can make smarter choices, if you want, allowing more sustainable choices or options.
Now that you mentioned smarter choices, and we also heard you saying a lot about environmental assessment, one thing that comes up when people hear about it is that it can sound maybe quite narrow. So building on what you just mentioned and how you explained everything for us, why is LCA considered more than just a surface level environmental assessment?
Thank you. I think that's a very good point, because you're right. When we talk about environmental assessment, sometimes we understand or misunderstand it as a more simple, if you want, green check. In reality, a proper environmental impact assessment, like the one LCA as a tool allows us to perform, helps us to go beyond, if you want, a surface level assessment. What does this mean? What makes LCA different, if you want, and more comprehensive, is that it looks at the whole system or the whole life, as we just mentioned with the example of the loaf of bread, over different stages in the life of our product or service. But also, very importantly, it looks at multiple environmental impacts at once. Instead of focusing on one single issue, like probably everyone has heard about the carbon emissions that are associated with climate change. This is certainly one. For in most of the studies we do, we look to up to 16 different environmental categories of impact. And LCA allows us to look at all of them, examining this range of aspects, which in turn allows us to identify trade-off. For example, we may do an LCA and identify a production system that allows a significant reduction in carbon emissions, but at the same time, it's increasing impacts in other areas like resource use or pollution somewhere else. So by capturing all these elements and all these connections, LCA helps us avoid what we know as shifting problems or impacts from one place or stage to another. So it's not so much about labeling something as good or bad for the environment in simple terms, but it's more about recognizing and understanding that most production systems are complex, that there's alternatives that may perform different and different categories of impact, and also identifying where improvements can be made that achieve a real and bigger difference in terms of environmental sustainability.
So what I wanted to know is if there are many steps or phases on an LCA study, and if you can explain what this consists of, so that we can understand better what happens actually, let's say on the ground or wherever this research is taking place.
Absolutely, yeah. So once you break down this methodology, we would find that LCA follows a very clear, standard, and quite logical path, if you want, that consists basically of four main stages or phases. First of all, you need to define the goal and scope of your study. This means defining what it is that you are assessing. We mentioned before, it can be an object, it can be a service, it can be a building, it can be a company. So you need to define that very clearly. You also need to determine why you are doing the study and what you want to achieve with this. Are you trying to assess the impacts of a specific production system? Are you trying to compare alternatives? Are you trying to find what you can change within your system to improve your overall footprint? All these aspects need to be thought through and established at this first step. Once you have determined this, there's another number of elements that are very relevant in this goal and scope level that have to do with the functional unit, that is the reference unit you're going to use to measure your product or service, but also the boundaries. We say life cycle assessment can take into consideration all the stages in the life of a product or service, but sometimes you need to adapt this to focus on aspects that are more relevant to your objective and your product or service. So you need to explain what you're going to be including and what you're going to be excluding and why. Once this is settled, the goal and scope, you know where you're going, you move to the probably most crucial step, which is building what we know as the life cycle inventory. This is where we basically create a detailed map of everything that goes in and out of the system that we are studying. For example, going back to our example of the loaf of bread. Here, we would need to identify and quantify all those elements that have to do with fertilizers, water, seeds, fuel used to grow the wheat, then all the electricity or heat that it's used in the mill to produce the flour and then to bake the bread, all the materials and the amounts you use to package it, to transport it, and then to sell it to the different customers. At the same time, you need to track for each of these stages you're considering in your study, everything that comes out. What is the actual product? We've identified a number of products at each stage. You have the wheat in the field, you have the flour in the mill, and then the bread in the bakery. But also any emissions that are generated at every step, whether to the air, to the soil, or to water, as well as any sort of waste that has been generated. All this information conforms what we know an input and output inventory, which forms the backbone and the essence of the LCA study, because it helps us capture the real or as close to real image of all the physical flows that intervene in the system and connect all the different stages of the life cycle. So once we've done that, we have as a next step the actual impact assessment, which nowadays is done mainly through a number of specialized software that make a number of calculations to translate all these flows, all these inputs, outputs, and their substances and emissions into environmental impacts in a way that we can assign a number related to each category of impact. That can go from climate change, different ways of eutrophication, acidification, issues related to human health, issues related to depletion of mineral or fuel resources, etc. Finally, based on all this, we need to proceed to make sense of these results, these numbers across a wide number of impacts. We need to analyze it, explain it, try to understand the drivers of each impact for each impact category, identify any trade-offs, and turn the numbers, if you want, into insights that can actually inform decisions.
While we're speaking, I was creating this image. So this is kind of a map or system where information and numbers and the insights come in and maybe come out later. I was wondering, because this raises some questions regarding data. None of this would work without it. So I was wondering, how do you actually go about gathering this information that is needed?
Perfect. Yeah, absolutely right. LCA it would be nothing probably without data. So yeah, it relies heavily on data. In practice, I like to define this a little bit, this process of acquiring the data, a little bit as a mix of detective work and careful and smart choices. Ideally, you start with what we call primary data. This means the real numbers and measurements coming from the system you're studying. What do we mean by that? We said in our inventories, we identify all the inputs and outputs, but we also need to quantify them. And this entails the amount of energy use, how much of each material comes into play, the level of efficiency of each process, and all this linked to the actual working of the system you're studying. In practice, beyond the ideal, this isn't always feasible due to the fact that sometimes there's not enough level of detail in that information. I give you an example, especially when we work in the agricultural sector. Most farmers know the inputs that they use. Sometimes they haven't measured exactly the amount of each of them. So this is part of the challenges that we face. So when it's not possible to have the direct primary data, we go and try to find what we call background or secondary data that comes from established LCA databases, or else from scientific articles that can represent a typical or average process as close or similar as possible to what we are studying. I would say that the key element here is transparency and consistency, if you want. So we need to be very clear about where the data we're using comes from, how representative it is of what we are actually studying, and where and which assumptions are made. So definitely LCA relies a lot on data, but I would say that in practice, it's not so much about having the perfect data everywhere, because unfortunately this is not always possible. It's more about making use of the best available data or information you have to build a quite robust picture and understand how strong the results are and where limitations or uncertainties remain. And this is important because we can see LCA also as a building process. You may have or do an LCA for a specific object with some important limitations. You'll make some assumptions, and this may help someone else later on to improve on this process. So kind of each LCA builds on what's been learned in previous studies.
Bruno, thank you very much for explaining all this. The example that you gave us before about bread and wheat data was very, very helpful to make us understand better what LCA is about. But now let's bring this closer to drones specifically and to Icaerus. So how common is life cycle assessment in the drone industry? Why is it an important part of the Icaerus project?
Yes, so in the drone world or field, as happens with many other, let's say, innovative technologies, the LCA is still more of an emerging, if you want, rather than very established practice. Most attention when it comes to drone has traditionally gone to other areas that are very important as well, that has to do with performance, cost, operation and maintenance requirements, safety and regulations. But not so much yet attention has been given to the environmental claims associated with these kind of technologies, which very often are based on a very common assumption, according to which small and electric automatically means greener, which is not always the case. It's a bit more complex than that. Let's say that the research community or the LCA community is catching up. There's more studies every year and reviews looking at different materials, the energy requirements, end-of-life aspects, what we do with all those components once they need to be replaced. However, and this is probably one of the main reasons LCA hasn't been used more widely yet when it comes to drones, there are still important limitations when it comes to the data available. We mentioned earlier on how essential data is for LCA. We see that there's still very limited primary data about drones. Remember, primary data is the one coming from the producers. Production of drones is relatively concentrated, and there's some reluctance to share all the details that we would need to do a first-hand LCA. But at the same time, because they are relatively new technologies, there's also limited background data in these specialized LCA databases. This is why it's not yet something you see, if you want, consistently applied across the drone industry at level of production and services. That said, probably this helps explain a little bit why it matters so much for the Icaerus project. The Icaerus project is about implementing real-world drone services in agriculture and forestry and rural areas. And Icaerus has made a point of explicitly using life cycle assessment to try and evaluate environmental impacts of these real-world drone services. Our idea here is for LCA to help us answer one very important or crucial question. That is, do drones actually reduce the environmental impacts overall compared to conventional ways of doing the same job? or do they just shift impacts upstream in previous steps or downstream after the life of those drones? Answering this question is very important, is essential, I would even say, to properly understand the potential that drones have to contribute to a more environmentally sustainable future, and how this can be improved. So yes, basically this is the idea what we're trying to do in the Icaerus project, and why we selected LCA as the tool to give us this full picture, or as full as possible, of the environmental footprint of how drones can be used in real life in agriculture and forestry and rural services.
So, staying with the Icarus context, when we talk about the life cycle of a drone, could you let us know what does that realistically include?
Yes, so when we talk about the life cycle of a drone, as we are trying to do in the Icaerus project, what we really mean is everything that makes that drone and its service possible. Following a little bit the logic we tried to explain before with the example of bread, it starts well before the first flight with your drone. And it involves the extraction and processing of all the raw materials that are needed for the different components that form this drone. This includes frames, motors, electronics, batteries, very, very important. Sorry. Then it includes all the steps and aspects related to the manufacturing and the assembly. Very important here as well, the energy you need for all these steps, the transport that is done for every part of the life cycle of the drone, and very relevant as well, the actual operational phase. That is the energy you use for charging the batteries that allow the actual flight to happen, all the maintenance and repairs required, any software updates, and any data processing linked to the flights, in those cases that some images are captured. In principle, the life cycle of a drone would also include all that happens at the very end of the drone's life. This means if each part is reused or recycled or disposed of. Within the Icaerus project, however, we only model end of life aspects, if you want, for components that are replaced periodically, such as batteries or other consumables. But a full end of life scenario for the entire drone with each of its components couldn't be modeled with enough detail. Instead, our focus remains on the use phase, when the drone is actually used and operated, and the service that it's providing. In our case, we have 5 different examples that, for instance, have to do with livestock monitoring or spraying. And we are trying to compare this drone service with the life cycle of a conventional alternative for doing the same activity. This approach basically allows us to capture or consider all the relevant impacts and understand how drones perform environmentally in real operational context as compared to realistic alternatives.
You just mentioned the batteries, so I will take the chance to ask you a bit more about that. From materials and manufacturing to battery use and the so-called end of life, what are the key components that are considered?
Yeah, so when we do this exercise of trying to unpack the life cycle of a drone, there's a big number of components that really come in, as I mentioned, all the materials, energy, and so on that need to come together to create this drone and make it operational. However, we can try and give like a summary so everyone understands what we're talking about. First of all, there are all the materials and the manufacturing. Again, this includes frames, motors, electronics, any sensors, all aspects that rely on metals, plastics, composites, and quite complex nowadays supply chains. Then another very important one has to do with the batteries, as it was mentioned, which is often one of the most impactful elements because of how energy and resource intensive is to produce this kind of element and how often it needs to be replaced. On top of that, next comes the use phase. That, as I said, is one of the focuses in the Icaerus project. Here comes the electricity that we need to charge each battery to allow the flight. We have all the maintenance steps and requirements and repairs that very often entail replacing different elements. And in many cases, there's also a digital side of things that have to do with data processing, storage, and software updates. In this use stage, a very important aspect turns out to be the actual lifespan of the drone. That is how many years of hours of flight you can actually use and operate this drone. And from our early results, we can see that the drone that is well or properly maintained and used for sorry, longer periods of time, it's somehow reducing considerably its overall environmental impact. And this is very important for us because this is one of the things that we wanted to identify and try to have a clear idea about. Finally, there's what we mentioned, all these end-of-life aspects, especially for components that, like the batteries or different parts that are more periodically replaced, where recycling or disposal choices can make an important difference when it comes to the impacts to the environment. Taken all together, all these elements show that the environmental performance isn't just about the technology in itself. It's not just about the object, the drone, but also about how long and how well it is used.
Bruno, this has been a great foundation to our conversation. Thank you very much for being here with us today. In our next episode, we will continue our conversation with Bruno from where we left it and unpack what LCA results can actually tell us about drones in practice, who uses these insights, and what this means for adoption in rural services. For those watching or listening, this episode was part of the Icaerus podcast series where we look at how drones are being assessed and used in real agricultural and rural contexts across Europe. More episodes are already available, with new ones coming soon. You can follow Icaerus on social media or visit the website to stay informed. Thank you for joining us today.